Okay, so now we're going to take some questions from the audience. And while we're waiting for people to put up their hands, I can ask a few myself. Oh, we've got one question from the audience here. So if you could say your name perhaps, and then direct your question to the...
Yeah, my name's John Wyatt. We've heard about proteomics, and we've heard about epigenetics. What would the panel say to proteomics being telling you about the disease you actually have, and maybe in very early stages as well, whereas epigenetics may tell you more about your future disease risk?
Caroline?
Yep, I'm very happy to respond to that. I think what came across in the presentations from both from a metabolite and proteomic sense was that they are useful both in prediction and understanding disease mechanism. I think epigenetics can add a further dimension to that. I think it adds an increasing dimension in terms of the disease prediction, because it has this aspect of being a historical archive rather than a cross-sectional snapshot of a particular metabolic or proteomic state. I think epigenetics can tell us something about disease mechanism as well. I think the field will be very aware of the debate around the tissue specificity of epigenetic patterns, and by measuring something in the circulating bloodstream, there's a limit to how much inference one can make about mechanism. But I think Chris's talk highlighted the value of connecting these molecular phenotypes to genotype, and how that can provide insights into disease mechanism. So if we do measure genome-wide DNA methylation, for example, we can look at the genetic correlates of that and then make inferences about disease mechanism as well. So I think there are pros and cons and strengths and weaknesses across the different forms of omic measurement, but measuring epigenetics can bring something to the table in both prediction and mechanistic insight.
Okay, thank you. I've got a question for Charlotte about the infection project, and it's really going to be fascinating to get all this data on antibodies from all the participants. But I wondered about stability of antibody levels over time in people, and how much is really known about that. And we've heard a lot with COVID that we have to have boosters every number of months because our antibody levels fall. So is this a problem in some infections, and how do you control for that in the analysis?
Thank you. Yeah, it's an interesting question. So we're basically mostly focused on the baseline samples, which were taken at sort of one point in time. UK Biobank does have some repeated measures. So we have started to look at repeated measures, which again are only taken at, so there's at sort of 2 time points. I mean, many of the antigens that we're looking at are actually sort of chronic infections. So they're things like herpes viruses. So say, for example, varicella zoster or herpes simplex, which tend to be things that are acquired early in life. And you might have periods when your antibody levels go up, when your bodies, if they start to reactivate, and then go down again. I think we're sort of happy that seropositivity is unlikely to change over time. But you're right in terms of the quantitative data. And I think that's something we don't know that much about. We don't have these very large serum samples sort of worldwide to be able to look at these dynamic measures. And it's something that I think would be great for the future. Yeah,
it's going to be really interesting. And I think another point about it might be that, you know, if somebody mounts a strong antibody response, it might mean that they're very good at clearing the infection rather than that they've had a high burden. And how we tease that out mechanistically to know what that means is going to be really interesting, I think, as well. So any hands up in the audience? We do have... we have... mic number 4.
Hi, this is Bodhayan, and I wanted to ask a question to Professor Wolf. I would like to know what's the cost of this single-cell multiomics that you guys are doing, and is there any plan to release that for UK Biobank? And if so, when we could see such a data in UK Biobank?
Sorry, I'm not sure I understood the question completely, but you asking about applications of single-cell multiomics to...
No, not application. I'm saying you showed us that you have developed in-house in Altos a method to do evaluate multiomics. And is there a collaboration with UK Biobank to release such a data?
Oh, I see. I see.
Yeah. And what is the cost of doing that multi-omics single cell?
So at the moment we have discussions a little bit. I mean, these are very early sort of discussions about maybe looking at epigenetic kind of assays in UK Biobank. And Valerie mentioned the single cell study that's being sort of supported by Chan Zuckerberg Foundation and Sanger. That's probably RNA-seq, single cell RNA-seq, I suspect. So I think for an application for multi-omics single cell to the biobank data, it's probably early days to discuss it, and we should discuss what the advantages could be in terms of what the samples are and the data that we could potentially provide. Yeah, I can't really comment on costs very knowledgeably.
Charlotte, would you like to, or Caroline, would you like to make a point on that as well from the population epidemiology side about the use of the data also?
I think one aspect of these really sort of highly technical, sophisticated multi-omic measures at a single cell level often require prospective collection of samples and tissues, and then they're not really amenable to biobanked previously collected and banked samples. So there are some assays that one can do on retrospectively collected samples, but I think that's a major consideration in how one might view the use of these in a cohort like Biobank in the future.
Mic number one.
Yeah, hi, Walsh, UCL. As a question for Charlotte Warren-Cash. You've got 46 antigens from 20 pathogens. How do you choose the 20 pathogens? How are you going to choose the next pathogens? And how are you going to hope to pick up pathogens you don't know are important yet?
Thank you. Some good questions. So we based our choice of pathogens on pathogens that had already been selected for the pilot study because we wanted comparable data. So we've added a few, but we haven't. We have tried not to keep it comparable so that we can build our resource. How were they originally selected? Well, there was a large panel of experts, and probably some people in the room were on this panel, who met several times to think about what would be the most valuable pathogens in terms of population-based research, and also what can be measured accurately, because obviously, the validity of the testing is imperative here. So I think for our study, we based it on the ID pilot study, but we have made a few tweaks as well, and we can continue to do so in the future.
We've got another question from here. Okay, mic number two.
A question to Heli. So those multi-metabolite predictions scores, the results are very striking, and you're kind of saying that, well, you're stuck with your genes, but your metabolomic profile you might be able to modify. How stable is that score? If you measured it on me today and then you measured it on me tomorrow, does it vary very much? What do you know about ways that I could modify that score? And are there any prospective studies that show that modifying that score might influence disease risk?
Yeah, thank you. That's a very interesting question. In general, these metabolites are quite stable. And for instance, our low-grade inflammation markers are very stable compared to, for instance, CRP, which often kind of jumps up when you have an acute inflammation. And also many of these lipids and fatty acids are very stable over time. But then again, they are reflected by, for instance, your lifestyle changes. And there are some studies showing, for instance, in dietary intervention, that even during like 4 or 8 week intervention, you do observe changes in your metabolic profile. So in that way, this can provide kind of very good means to also follow up your change and see how this kind of choices that you make, if you do lifestyle intervention or you start exercising more, you can really see the impact that it has on your metabolic profile. And that is so great about this kind of risk scores, because then you're not stuck with it, but you can still modify it. And even if you would end up having, for instance, hypologenic risk, we have also shown that you can actually modify that risk by this kind of biomarker risk scores. So in a way, it provides a very valuable mean to kind of see what is really going on in your body at the moment.
Comment from Caroline?
Yeah. Did you stratify by statin use in terms of the population?
Yeah, we have tried that also. And also now that we have these 300,000 samples in the UK Biobank, there's like lots of different subgroup analysis that one can do. And we have also looked at different age groups. And for instance, the younger individuals where they're not yet using statins. And we do observe sometimes even stronger results in those groups.
Okay, so we've got microphone 3 here in the second row, and then we'll go to the gentleman in the blue shirt in the middle.
Hi there, I'm Michael. Question probably for Chris and Heli. Regarding the data, obviously we have a large volume of individuals, of participants, up to 500,000. For proteomics, for whole genome sequence, for all these data sets, they're especially wide. And from a kind of machine learning perspective, which is where I've kind of been working, there's a massive challenge with the kind of P greater than N and how you can kind of learn new associations without a priori assumption. I just wondered if you'd kind of come across this, what you think the kind of cutting edge approaches are which can kind of deal with some of this challenge, and yeah, what you think the future in general of machine learning in this space is. Thank you.
Great question. Do you want to go? Sure.
You can both answer it.
It's an excellent question. Honestly, the answer is that we're currently looking into it. Everything from basically logistic regression, elastic net, all the way through, and we're seeing what method gives us the best AUC. Is there redundancy in the data? Obviously, there's going to be proteins that are highly correlated. So yes, we are looking into it. Really, as you saw from my talk, we started with the low-hanging fruit. Let's do GWAS, and now we're going to look into the more interesting questions. So, Heli?
Yeah, I mean, it's the same for us. We have also tried lots of different methods, but it was also great with the kind of UK Biobank and having such a large sample size is that often even the kind of simpler methods give very similar AUCs and very similar accuracy to then more complicated machine learning methods.
Okay, thank you. So, gentleman in the blue shirt is next. So, microphone 3 again.
Great. Chris Southam from MDC. I had a question for Charlotte in related to the speed of possible response. One of these is obviously this pandemic preparedness aspect. The other is, of course, could you now rapidly tool up to look at the Staph A that's caused the 6 fatalities in the children? I know the Biobank hasn't got young cohorts, but is there anything you could do quickly?
I think it might be challenging to just thinking about the sort of different age groups of the population and the fact that his samples are historically collected. I mean, I suppose for pandemic preparedness or looking at outbreaks in general, what we need is mechanisms to... We've already got a great cohort in UK Biobank, but I guess you need mechanisms to be able to jump in and collect data in real time almost, so to collect new data. So we probably couldn't do it historically.
And just from an epidemiological perspective, integrating these sorts of serum-based surveillance methods, I think, give a fantastic baseline for such sort of responsive mode preparedness in relation to a new infection. So I think it's, the novelty around large-scale serum-based antibody measurements is fantastic. It's a sort of new era in terms of documenting historical patterns of infection, and that in itself could be really beneficial for how we move forward and respond to future infection waves.
Yeah, I mean, this is a classic disease of childhood, isn't it? So would you assume that there's going to be titers or high levels of reactivity against this in the population in UK Biobank anyway, that you're going to see this? But it's not part of your screen, is it? No. Okay, so microphone number 1 down the far end over here.
Okay, thank you. My name is Richard Boabin, and I'm a scholar at St. Mary's University studying bioethics and medical law. My question is specifically to Professor Wolf. May I know some of the ethical conundrums or hurdles that you may face that you are facing in terms of the work in epigenetics, and perhaps it could also go around to the other participants. What ethical conundrums you're facing in your research work?
That is a big question. I think maybe as an example, of course now the field, and we're thinking about rejuvenation of human cells and human tissues, and potentially even organisms. So certainly this is possible in model organisms. And I think that raises very important ethical questions about what is it that we want to achieve. You know, you have sort of two sort of polar options there. Do you want to extend lifespan, or do you want to extend health span, for example? Those things raise very, very important ethical questions, and we've been debating this and are debating this in our new organization. I think for us, the most important thing is to help with extending health span in the population, and yeah, I think it's an ongoing, very important question. Thank you.
I mean, it was interesting how you were proposing, you know, the drug or the druggable approach is Cas9, and if you're thinking about health span, it's across multiple organs in people as they age. I mean, that's a really visionary way of trying to improve health, is Cas9 approaches. What's the current thinking on how applicable that's going to be?
Yeah, I think that's a difficult one because, you know, there's so many loci in the epigenome that you would have to consider changing, and what are the driver ones, what are the, you know, the follower ones, how many would you have to target? It's a very important question, and how, you know, how realistic that approach is in terms of therapy in the future. We will have to see that. There's probably simpler approaches initially based on, you know, Yamanaka factors and derivatives at this point in time to restore cell health and rejuvenation and cell health, and that's what we're focusing on at the moment.
Okay, thank you.
Would you perhaps do that in an organ-specific way to counter, for example, liver fibrosis or beta cell degradation in the pancreas, for example?
Absolutely. I think there are sort of ex vivo ideas where you can just take the cells, improve their health, and then transplant them back. That's sort of cell therapy kind of stuff. But then organ-specific approaches may be coupled to organ transplantation. I think this could be an interesting avenue to think about.
Okay. I had another response to the question about ethical issues. I think the argument for the ethics of knowing one's genetic makeup is well rehearsed. You can extend that perhaps to some degree to the molecular phenotypes we've heard about today, so measuring one's proteome or metabolome or epigenome, which some of those measures give a snapshot of current status, and some of those give an archive of historical exposure. So the ethical issue that sort of presents is, to what extent do you want the knowledge of your exposure history in terms of what DNA methylation signatures might tell you, that they might tell you about your infection history, inflammation, smoking history, whether your mother smoked while you were in utero. You know, it's all sort of relatively or quite personal information, perhaps not as deterministic as your genetic makeup, but still carries with it, I think, some ethical considerations.
Okay, so before we finish, I'll take a question from the online audience, which is around proteomics, and I also have a question as well for Chris. So the online question is, how accurate are the concentrations provided by the Olink platform? There's lots of data looking at reproducibility, but when you try to validate Olink Quant with other platforms, SomaScan, MassSpec or ELISA, there's significant discrepancy. Are you validating some or all of the measurements?
Yeah, that's a good question. I would say, in order to validate, I mean, it's a huge assay. So there are 3,000 proteins, almost 3,000. So in order to validate each one, it would be far too expensive, far too labor intensive. We have looked at specific examples of proteins that have been measured via ELISA or Quanterix, let's say, etc., and the protein measured via Olink. And generally, we see, good correlation. It's typically, 0.7 or higher in terms of correlation. It is important to point out that the Olink measurement is relative. It's not an absolute measurement. So even seeing those kind of correlations based on a relative measurement against one of the gold standards is quite good. In terms of the comparison against the affinity-based approaches, the Olink and the SomaLogic, that's the top question that always gets asked, and my answer gets more nuanced every time I'm asked. There's strengths and benefits to both. I think that Claudia Langenberg published a fantastic paper showing that you get synergistic insights from the different platforms. It shouldn't be so much about putting them head to head, so much as what kinds of information can we get from one versus the other. I would say the aptamer-based approach is very good for looking at patterns of disease because it captures so many proteins, whereas I think that the antibody-based Olink approach is quite good for drug target discovery because it has that degree of specificity. So it is a little more nuanced than which is more accurate because it really just depends on the use case.
Yeah, I mean, I've got one question, which maybe it's more of a comment, and I think thinking about where we go further forwards with proteomics is that these assays, I assume, they're not taking into account the amino acid sequence. So if you get variations due to polygenic changes or whatever, you're not going to pick that up. So you're measuring the level of the protein, but not the activity and its ability to do its job, and how that's affected is going to be really crucial in its role in disease. So how do we get proteomics to that level where we can not across 3,000 proteins, obviously, all in one go either? I mean,
no, I love that question. So we obviously the affinity-based approaches are gathering a lot of popularity because they're high throughput. But of course, you have mass spec, and that does capture post-translational modifications and goes a certain degree deeper. Traditionally, mass spec has not been high throughput. There are some companies now claiming that they can make it more high throughput, and to that end, it hasn't been officially launched yet, but the Pharma Proteomics Project has put in a proposal that was approved by UK Biobank to apply 3 different mass spec-based platforms and SomaLogic in the COVID-19 imaging sub-study. So this is going to be about 2,500 samples, 1,250 participants, so longitudinal. And we'll look to see what kinds of insights do you get from these mass spec platforms versus the SomaLogic versus Olink. So that should hopefully come online soon.
Okay, thank you very much. So I think we're looking to wrap up. I'm being waved at from Jenny over there. So thank you very much, everybody, for a great session. Thank all the speakers for their excellent talks, and I think we follow this with lunch.